So, we have seen now how the experiment can be performed to measure the ECG signal, right. Now, so the idea here is that if you know different circuits and if you know how to place them together, you can use this entire unit for as a signal conditioning unit for different applications. One such application we have shown it to you, which is ECG, but you can also use it in EEG, right. You can because the difference there is that the signals that are at the output are in microvolts, when in ECG the signals were about few millivolts, right. So, it is a little bit trickier when we talk about the signal conditioning unit for EEG. However, we will see the EEG platform in one of the cases, but not for this particular course. However, let us see how can you use some other electronic system to measure the force sensor, the change in force sensor, and how can you can display it using a controller, right, on the screen. So, the point is, if I apply a certain amount of force, that force should correspond to the that force I want to see on my computer. So, what is the electronic module? So, here you can see the first thing that we are using is a Wheatstone bridge, right. We have seen the advantage of Wheatstone bridge over potential divider. If you do not know, you can just quickly see that why we are opting for Wheatstone bridge instead of a potential divider or a resistive divider circuit. So, right, this is a resistive divider circuit, and if I have this resistor as sensor resistor, this is a fixed resistor R equals to RS when there is no force applied, right. If I apply 5 volts as a supply, then what is the output? Output starts from 2.5 volts, right. Output starts from 2.5 volts, right. So, now if I go for Wheatstone bridge, I can use the entire signal from 0 to 5, and here I am limited from 0 to 2.5. Thus, we have to use Wheatstone bridge over the potential divider or a resistive divider circuit. Now, if I have a sensor that will show the change in resistance, right, on applying a force, right, then it can work as a force sensor. Now, this force sensor can be a piezoresistive sensor, right. So, let us see that if I have a sensor that changes the resistance, how can I and that resistance is because of the force, how can I display the force on the computer. So, first block diagram in this particular block diagram for contact force measurement, the first block is of Wheatstone bridge. Then the output is connected to the instrument amplifier and voltage follower, which is further connected to the data acquisition system. Here we are using SenseRay model 626, but you can use another controllers as well, and finally you are displaying the output in terms of force versus voltage. You can also show in terms of what is the value of the force that you are applying on the sensor. So, we see the block diagram of contact force sensing system and the circuit diagram. This is a circuit diagram, right, where you can see the instrumentation amplifier. This is a Wheatstone bridge, right, this is also a Wheatstone bridge, and then you have connected it to an instrument amplifier followed by a voltage follower, right, and this voltage follower is connected to the sensor array, and the sensor array is connected to the system. So, here you can see that there is RO and RO, these are fixed resistors. This RS and RP represents the resistance of the fabricated strain gauge and a potentiometer respectively. Okay. So, in fact, what we can do is we have to also use this as this particular symbol, because resistance would change when you apply given amount of force. Right. So, this is how this signal conditioning circuit can be used when you want to measure the force, but let us now see quickly how the piezoresistive sensor will work. Because finally you are designing a system that can be used for piezoresistivity. Now, the first question to that comes is why we want to discuss force sensing in the course, which is focusing on electronic systems for cancer diagnosis, right. Because we are interested in understanding the tissue elasticity, and you can understand the tissue elasticity when you apply a certain amount of force and you see how much force is actually translated to the sensor sensor, and based on that you can understand whether the tissue is stiffer or is less stiffer or more stiffer. So, that is indirectly we are talking about the tissue elasticity, right. So, but how the sensor would work and how can you fabricate this sensor. So, let us quickly see how can we fabricate the sensor and how sensor would work. So, if you see the screen, what I will do is I will just have 2 more slides, so that is easier for you to understand, and I will quickly show it to you how can we fabricate such a force sensor, right, using a standard lithography technique, right, and then we will end up this particular module. Okay. So, let us quickly see photolithography. Photolithography right. So, we have seen photolithography techniques, right, in the earlier modules, right. So, I do not want to get into too much detail in this particular module, but using photolithography you know that I can design a strain gauge, right. I can design a strain gauge. These are the strain gauge, this is the contact pad, right, and then you have the PDMS. Let us say you have a bump. Now, if I apply a force, what will happen? This diaphragm will bend. So, this will have this effect. Right. So, this bending, because we are applying a force, right, this bending causes change in resistance, right. This is schematic 1, this is schematic 2, and because of the source there is a bending like this. This bending will cause change in resistance because there is a strain on this strain gauge, and there is this change in resistance we can measure with the help of a multimeter, as simple as that. We can use a multimeter to see the change in resistance, right. Now, what is this? So, this is, I have to just draw oxide, right, because we cannot have metal on semiconductor, we all know, right. We all know that we cannot have metal on semiconductor. So, now what we are having? We are having a thin layer of oxide to start with. So, the process is like this: there is a silicon wafer, then we grow oxide, right, which is our silicon dioxide. Then the next step is I am depositing a piezoresistive material on this particular oxidized silicon substrate, and then I am performing photolithography. When I perform photolithography, I will have the pattern that I am interested in. After that, I will deposit, I will take another silicon wafer, right, create a well like this, right, oxidized silicon wafer, create a well. Now, why I am running faster? Because I am assuming that now you guys know very well what we are talking in terms of microfabrication. How to create this well is very easy. Again, you open the window, you etch silicon, right, open the window, etch silicon, and you get this mold. What I mean by open the window, etch silicon, suppose this is your SiO2, this is Si, this is SiO2, right. Now, if I want to get this particular pattern, what will I do? I will, let me go quickly to the steps. First step that I will do is spin coat positive photoresist, right. Next step is I will perform the soft bake at 90 degree 1 minute. Next step is I will expose the wafer, right. I will expose the wafer such that I can create the window on the oxidized silicon substrate. This is my mask. This is what kind of mask? It is a bright field mask, bright field mask. This is bright field mask. Then we will expose the wafer with UV light, right. After that, what we will do? We will develop the wafer. When you develop the wafer, what will happen? Expose the wafer, then we will develop the wafer. When you develop the wafer, the photoresist will stay in this area, right, because this area was not exposed and this is a positive photoresist, correct. Now, what we will do? We will dip this wafer in BHF. When we dip this wafer in BHF, what will happen? The oxide will get etched, right. The oxide will get etched like this. Correct. So, what we have here? We have a positive photoresist and here we have silicon dioxide. Right. If you have observed, the oxide from the back side also gets etched because it is not protected with positive photoresist. Next, what we will do? We will now strip off the positive photoresist. Strip off of positive photoresist can be done using acetone. That means that if I dip this wafer in acetone, what will I have? I will have this particular pattern, right. SiO2 will not be affected, right, and the photoresist will be stripped off, correct. Now, the next step is I will go for DRI, deep reactive ion etching. What will happen? It will etch silicon, and it will give me a step, correct. This is what I want, why? Because now the next step would be I will pour PDMS, cure it and take it out. So, what will I have? I will have this structure, correct. I will have this structure. Now, I will cut PDMS from this side. So, what will I have? I have a bump. This bump I will attach to my piezoresistive material. This bump I will attach to my piezoresistive material. So, let us say PDMS, let me show you in this particular pattern. This is my PDMS, right. This is like mold. So, whatever is there in the mold, the reverse of that will come in the PDMS. You have seen this thing in the microfluidic design in the actual experiments that we performed in the lab, right. So, it is easy. So, now after if I cut it, then it becomes like this particular bump. This I will attach to the strain gauge, and then what I will do? I will do the same lithography and I will open a window from the back side. I will open the window from the back side. What does that mean? Let me just show it to you. I will have I will remove silicon dioxide from the back side and then I will do DRI, right. I will do DRI, and when I perform DRI, what will happen? My silicon will get etched to get me the piezoresistive sensor. Now, if I apply force, then this diaphragm will bend, and depending on the force, there will be change in the resistance in the piezoresistive sensor. Now, how we are going to understand or use this particular sensor to understand the properties of tissue. So, that is the question. So, if you see what we can do, we can place a tissue on this particular sensor. Let me just quickly remove these things. So, now our idea is that we place a tissue is from the biopsy, right. So, it is like a cylinder. If I place a cylinder, right, on this sensor like this, right, and now if I apply a force, right. So, the amount of force that I am applying here and the amount of force that my sensor is able to measure, that depends on, or the amount of force that I am applying here and the amount of force that is translated to the sensor, that depends on the elasticity of the tissue, right, elasticity of the tissue. So, if the tissue is stiffer, right, less amount of the change in the translation of the force would be different, and the tissue is less stiff, right, is more elastic, then correspondingly different force will be translated to the sensor. So, what I get from this, what literature shows that as cancer progresses, as the disease progresses, the tissue related cancer progresses, there is a change in the elastic property of the tissue. You may know that the people who suffer from cancer, and if there is a tissue related cancer, the tissue becomes harder. That hardness is the stiffness, right. So, it will be less elastic. So, now that elasticity we can measure with the help of this particular sensor. How? Because I am looking at the change in resistance. So, how can I use this particular change in resistance and understand what is amount of force and how to change it to elasticity, right. For that we have to go for the electronic module, and that is why the signal conditioning system that you have seen in this particular slide, if you can see the slide, right, is the one that we have to use for understanding the force sensor. Now, I have here shown you for the catheter contact force measurement, but you can also use for the tissue elasticity measurement as we have discussed in the slide. Right. So, this will be the last slide for this particular module. If you have any questions, feel free to ask me, ask the ask in the forum, and I will be very happy to address your questions. If you further have any comments, or you are really stuck with some of the parts where you are not understanding, please feel free to also email me. Alright, I will try to respond to your email as soon as I can. The point is, here we are understanding how can we bring different aspect of the circuits, integrate it together, and to apply it to understand the change in the tissue property and correlate it with the cancer progression. Right. So, this can be an interesting study if you study the change in the elasticity as cancer progresses. So, that is one research problem for you. So, this is the last slide for this module. I will see you in the next class. Till then, you take care. Bye.